Welcome to my talk, Babashka, a meta-circular interpreter for the command line. I'm going to explain what that means in this talk. My name is Michiel Borkent. I'm from the Netherlands. My name on the internet is Borkdude. I made that up when I was 20 years and then I was stuck with it. And okay, a little bit about Clojure and me. I met functional programming at university. I was introduced to a language called Miranda, which is a predecessor to Haskell. And towards the end of my studies, I was introduced to Common Lisp, which is a Lisp, obviously. And I like both approaches. And actually, Clojure combines those two approaches, functional programming and Lisp. When I was a CS lecturer for a while, I had to teach Java to students, and I took Clojure as an opportunity to learn more about the JVM. Most people already know the JVM and then go to Clojure, but I went the other direction. And so Clojure is a Lisp on the JVM that emphasizes functional programming. Oh yeah, by the way, when I did Common Lisp, I thought I was doing functional programming, but I kind of missed the point of immutability there, which is like the big difference that Clojure brings to this. I tried many other languages. I used Haskell. I even have Haskell running in production still, like a hobby project. PureScript, Scala, but at the end of the day, I just love working with Clojure. It makes me happy, and also I can make a living from it, which is a nice thing. You can actually use it for work, something that you love, and you can use it for work. It's a perfect combination for me. And I want to use Clojure's standard library everywhere. I just love how elegant the standard library is. So a question, is Clojure dead yet? It's commonly asked on or discussed on Hacker News. Just a few thoughts. In the last 2 years, I've been making a modest income from doing Clojure open source work through sponsorship on GitHub sponsors and other channels. So if Clojure was a dead ecosystem, it's a miracle that I can make an income from that. So there exists something called Clojure is Together, which is an organization which supports Clojure open source. They funded quite some amount of people. There is a company called Nubank, which is the largest online bank in South America, which has more than 1,200 Clojure developers. You don't hear a lot about this like on Hacker News maybe, but it does exist. There's many other companies which have Clojure at central to their technology stack. I'm not going to name them all, but okay. And once you know Clojure is a small language. Once you know the standard library well enough, you don't ask that many questions on Stack Overflow for the reason that maybe the question has already been asked 10 years ago and it's still valid today because Clojure doesn't change that fast. And also that Clojure has a very tight community. There is Clojurian Slack where there's like more than, I don't know how many people, but thousands of developers are discussing things over there. So before your question even reaches Stack Overflow, it's probably already answered over there. And it's a small language that certainly helps. And most questions, by the way, are not about Clojure, but about the host system that Clojure is sitting on top of, like the JVM or JavaScript or things like that. So Clojure doesn't make breaking changes. So code that worked 10 years ago still works today. And that's ideal for long-lived, stable projects. Like the JVM itself, it's a very stable platform. And so there's not much hype around Clojure. It doesn't change that it doesn't make any radical changes. So Babashka is a sub-community within the Clojure community, and it even has its own conference. I'll show a picture at the end of the the presentation. And so long live dead languages, I would say. Okay, so what is Babashka? So here we see an invocation on the command line, bb -e plus 1 to 3, and then it spits out 6. So this is a Clojure expression, and it only takes 13 milliseconds to run. I mean, it depends on your operating system, but this is kind of the range that you can expect. And it's a native Clojure scripting tool. It's a single binary, and you don't need an additional JVM to run this. But it does implement a large subset of the same JVM Clojure that you're used to, or that many people in the Clojure ecosystem are used to. And you can use this tool to replace the gray areas of Bash. When I'm writing a Bash script with nested if-else, that's already where I feel that I have to look up documentation. But if I would do it in Clojure, it would be very natural for me. So Babashka is focused on Clojure developers that need scripting in their projects and don't want to change languages. It's easily installable via multiple package managers. So this is the main problem that it solves. On the top, we see Clojure on the JVM that just executes an expression. It doesn't really matter what the expression is here. But this is just the raw startup time that you get with a normal JVM and Clojure. It takes about half a second on this very laptop. If you have a lot of dependencies, like the Babashka project itself has a large number of dependencies, it can already take 7 seconds. So the more dependencies you have, the longer it takes. But with Babashka, it only takes 22 milliseconds, and all these dependencies are already available. So how is that possible? First, we're going to look at an example script to give you an idea what kind of scripts you can create. So here we're compiling some Java. Of course, we're not using Maven, but we're writing a script to do it ourselves. I mean, this is just an example. So we're comparing a class file here to a Java file, and if the Java file is newer, then we're invoking javac, and else we're just skipping it, and we're not paying like the startup cost of javac. So it's a very simple script that you might do with make, or but in this case you can do it with Babashka. Another example script. Here we write a script to show what's the current time in the Pacific time, standard time. And you don't have to understand these details, but the main idea is that you can also do Java interop with Babashka. So it's not limited to like just calling Clojure functions, but you can do Java interop like you can do in a normal JVM. And this still is instant on your command line. Of course, as Clojure developers, so if we have like this verbose Java interop, sometimes we like to hide it behind the library. Oh, by the way, I should tell, this also works on Windows, so not only on Linux. Like Bash scripts tend to be written for with Linux in mind, but all the scripts that you write with Babashka also work automatically on Windows because it's built on JVM technology, and JVM technology is built with cross-platform in mind. Okay, here we see the same script, and now we're adding a library from the Clojure JVM ecosystem to our script. It's called tick, and then we on the last 2 lines we call the tick library and do the exact same thing. So this example is showing that you can reuse libraries that were written for Clojure JVM in Babashka, and we can reuse this ecosystem. So you don't have to start a new ecosystem. We can tap into the existing one. So in Babashka, there is a large number of libraries included that you would typically need for scripting, like command line parsing, CSV, XML, YAML, HTTP. There is an HTTP server, HTTP client, etc., etc. So things you would typically need are already provided for you. so you don't need to pull those in from the ecosystem. But, okay, there is a risk of including these libraries, because in the Clojure ecosystem, we tend to value not making any breaking changes. Like if you write a library and you upgrade this library, the user should never have to change their code to keep the script running. And this is a little bit different than some other ecosystems do, like for example so there is this idea of semantic versioning, that if you release version 2 of your library, it's okay to make breaking changes. But in ClojureScript, we have another way of solving this, is by just renaming your library or providing different namespaces for version 2 while keeping version 1 in place, so users don't experience these breaking changes. But when including these libraries in Babashka, there is the risk that I am including a library that makes breaking changes, and that in turn could break existing Babashka scripts. So I'm trying to work together with the library authors that it doesn't happen, but in general, in the Clojure ecosystem, this is a high valued principle. So and also for me, once a library is included in Babashka, I also cannot remove it, because this would break things, even if the libraries or some functions are deprecated. So imagine Unix command line tools changing their output every year. Like we have LS version 2 now, and it outputs JSON, and it's awesome. But so you cannot really build a platform on top of that mentality, right? If you want to know more about that culture, you can watch the speculation talk by Rich Hickey, the author of Clojure. It's worth checking out. Okay, so there is a large number of other libraries that you can use from the Clojure ecosystem, just as an external dependency, like I showed in that example where we used an external dependency. This is not an extensive list, but just to show that there is a huge overlap. There is a Clojure test runner built into Clojure itself, which is also part of Babashka. When is the last time that you wrote a test for Bash script? For me, it's probably 8 years ago. But for Clojure code, I tend to write tests. So that's also a nice benefit of using this language for scripting. So how is this possible that we have this fast startup? So I'm using a GraalVM native image, which Thomas showed or spoke about in the last talk. And the awesome thing that I find is that you can build command line tools with instant startup from existing Clojure JVM technology. 2 examples that I wrote prior to Babashka is one is called Condo. It's a linter and static analyzer for Clojure. And it's just also a single binary. You can throw some Clojure code at it, and it spits out some warnings about it. So this was prior to Babashka. And the other tool is called Jet, or one other tool. There are many more, but and you can convert between JSON, Eden, and Transit. And there is a query language, so it's kind of similar to JQ. So here we see Condo in action. On the left, we have a piece of Clojure code. It's a function foo, which returns a number. And then on the next line, we see first foo 10. And it gives a type warning because foo returns a number and you cannot call first on a number. And that's what we see on the right on the second line. It says expected seekable collection, but I received a number. And there are some other warnings there. So that's what Condo does. It analyzes your code and spits out warnings. And also it can return just data about your code, so in addition to warnings. And this is used by the Clojure LSP tool to implement the LSP protocol for Clojure. So the LSP protocol can be used to provide navigation and renaming and stuff like that for your editor. That's also done on top of Condo. So the other tool was called, or still is called Jet. And it's a tool to to either transform or data or query data. And initially I wrote a DSL thing for this to query your data using a Clojure-like thing, Clojure-like language. But I didn't like the fact that it was like Clojure and not Clojure itself. So eventually I started wondering, can I implement, can I evaluate just some Clojure instead of this DSL? Okay, so here we see an example of the simplest way of trying that concept. This is like the simplest implementation of Babashka. We have a main function and we get the second argument, which is this +123 argument. And then we call load string. And in Clojure, load string is a combination of parsing the Clojure code and then evaluating the Clojure code. But if you try to compile this with GraalVM native image, you get an error message about bytecode that has not been predefined. Basically, it cannot turn the bytecode into machine code at runtime because native image does this ahead of time. And you can maybe now feel the challenge coming up. So how do we replace load string with something else that does work inside of a native image so that we can still have the fast startup, but still can dynamically evaluate some Clojure code? So a famous language researcher called Thomas Wertinger said, constraints force creativity and innovation. In the previous presentation, actually, he said that. And that's, in my case, that inspiration is called the small Clojure interpreter. So this is what basically replaces load string. It works inside of a JVM, inside of a GraalVM native image, but also in JavaScript. And it supports sandboxing, which is a nice bonus feature. It's not strictly necessary for Babashka, but it's just a nice to have, basically. It works inside ClojureScript advanced compilation. If you don't know what it is, it's a way of making the output, the JavaScript output of the ClojureScript very small, but it does very aggressive optimizations. A bunch of renaming going on. And so the interpreter can be used in combination with those aggressive optimizations. And it supports almost all of Clojure, not all of Clojure, and this has to do with limitations of those environments, or mostly native image, where it cannot define new Java classes, like at runtime. There is some support for this, but this is like a gray area of this approach. This interpreter is online on GitHub, open source under the Babashka organization. And this is an example. So here we call the interpreter with a function, or a string that contains a function. And then we get back a function, and we can just call this function in our host environment. There is no weird proxy thing going on that you have to convert between data types. It's just regular Clojure function that you can call from Clojure. By default, SCI only exposes Clojure core. So if you want to add libraries, like I did in Babashka, you have to create a configuration. So you say you have a map called namespaces, and then a key Cheshire.core, which is a JSON library in this case. And then we expose the generate string function. And then we pass the JSON generate string function from our host environment. And if we provide this configuration to Sai, we can execute the same expressions as in our host environment, but then under the constraints of native image, let's say. So Sai is a meta-circular interpreter. What does that mean? So Sai implements language features of Clojure in terms of host Clojure's own language features. So, and there is even a more strict definition, which is self-interpreter, where the interpreted language is the same as the host language. So I'm implementing Clojure in Clojure, but you could, for example, also implement Python in Clojure if you wanted it. But this is a self-interpreter. So, for example, function application can be implemented using Clojure's apply function. That's not the most performant thing to do, but that's a good start. And for example, loop in Psy is implemented in using loop in Clojure. But pure functions like plus and assoc, so pure as in they don't cause side effects, can just be direct references to the host functions because there is no point in re-implementing those. We can just use them. But side-affecting functions often are re-implemented, like creating namespaces or defining functions to make Psy sandboxed, which again is not strictly necessary for Babashka, but it's just a nice to have. So here is an example of how you can implement a meta-circular function application in a couple of lines of Clojure. So in Clojure, we always start at the bottom of the code. So we start reading in the comment form. Comment is a way in Clojure to not evaluate this when the compiler sees the file, but you can evaluate this from your REPL using interactive development. So we have this -eval invocation, and then we pass it a map, which let's call it the context. And we set the current namespace to user, it's just a name. And then we define some namespaces, user, and then a function foo, and then the function is a function of 3 arguments, which adds those up. And then we evaluate the expression foo1 to 3. So we evaluate this thing, and we get back 6. So what happens is, if we pass this expression to the -eval function, we check if it's a list-like thing, which is done using the seek ? Function in Clojure. And if that's the case, then we go to apply, -apply. And in -apply, you see that I reused Clojure's own apply function to apply the function that I look up using -resolve in the context, and then also evaluate the arguments. So this is a very simple, not the most performant way of doing it, but okay, to get things working and to see if things actually work in GraalVM and to see if, like version 0.0.1, it's good enough. Let bindings, similar approach, but let bindings cannot reuse Clojure's let directly because let in Clojure is a very static feature. You cannot say, okay, yeah, it's just too static to reuse in the interpreters. You don't know beforehand what kind of let bindings the user is going to provide. So instead of doing reusing Clojure's let, we're going to use an immutable hash map, which is just a map of symbols to values, and we just store the locals, the let bindings in there. So we start at the bottom again. We call -eval with an empty map, and then a let expression, let x be 10, and then we return x. Okay, so we go to the -eval function. Then we check if it's a seek, and if the first symbol is a let. If that's the case, we go to -let. We pull out the local symbol and the value, and we evaluate the value, and then we store that value in the locals map, which is part of the context. And then we evaluate the body of the let using that context in scope. And if it's actually, if the expression is a symbol, which is the body of the let here, then we call -local, and that just gets the local out of this map that we constructed using the right value. So this is, again, a very simple approach in one slide. A little bit more challenging is lambda, so function creation. Again, we have, on the bottom, we have a -eval invocation. We pass an empty map, which is the context, and then a function expression, which has 3 arguments, and we just return the last one. And then we call f1 to 3 on the function that we got back, and that should return 3. So again, we use, in the context, we use a locals immutable hash map for this. And you can see that the -fun function reuses actually Clojure's own fun construct. Okay, so this is the naive approach, let's say. So we parse an expression, and then we throw the expression at the interpreter. So let's say we're evaluating +1x, and so that gets us back a list of a symbol plus a number 1 and the symbol x. So if we're going to evaluate this, you can see in green that we're doing a lot of work just to evaluate this expression. But suppose that we're doing this inside of a loop. So let's say we're evaluating this expression, 4x range and then a large number, and then we're evaluating +1x. Every time we're evaluating +1x, we're looking up that the symbol plus refers to a function in Clojure core, and that 1 is a constant, and that x is a local, and so actually everything that is in green, we could do only once, and not every time we visit this expression. And the things in purple, that's the only thing you actually need to do at runtime. So there's lots of optimization to be gained there. Actually, this approach is also described in the book Structure and Interpretation of Computer Programs, chapter 4, if you want to know more about this approach. And so basically, Psi splits up things into an analyzer phase, which we see on the top left, and an evaluator that then evaluates what the analyzer returns. So the idea is do as much as possible on the left, and then do as little as possible on the right when you actually evaluate these nodes repeatedly. So instead of doing this walking of expressions and then directly evaluating them, we turn this +1 to x expression into a data structure that knows how to evaluate itself very quickly. And then, so that's where a lot of performance comes from. Okay, so initially that was not the goal. At first I wanted to know, does this approach actually work? And then later on I started to optimize stuff. So for example, here we have a loop of 10 million iterations with 1 conditional and 3 function calls. So we have 2 counters, and we check if one counter is positive. If so, we do a recursion with the incremented value of the one and a decremented value of the second one. And so in SCI, in native image, this runs in a little bit more than half a second. Compared to JVM Clojure, this is very slow, but there is just more overhead in the interpreter. But let's compare it to Python, for example, which is also an interpreter. Then it's actually faster. So this is the same example, but converted to Python and ran on the same machine, and this is almost 900 milliseconds, while in SCI it is a little bit under 600 milliseconds. So if you're wondering, does Babashka, which is based on this interpreter, is it fast enough for scripting compared to JVM Clojure? Well, if Python is fast enough for you, then Babashka is probably also fast enough for scripting purposes. So initially, the very naive approach is on the left. I started measuring old versions of Babashka that ran this loop example. First, it took 16 seconds. And this is measured in Linux on a different machine, by the way, but lower is better, so it's all relative. And right now, this example runs below a second on x64 hardware. And so one thing that really helped was splitting up analysis and evaluation. But there is another thing that really helped was not using immutable hash maps for these locals. So for example, here we have a function which is actually a closure. So it closes over the values a and b. And it has one argument. And in the body of the function is a let expression, which also has one binding. So those are 4 things you should store in this hash map. So it's a dynamically stored hash map that now has 4 things. But we can already statically see that it only needs 4 things. So if we manage to replace this immutable hash map by an array with only 4 positions, it's actually 15 times faster. And so the immutable hash map approach is very elegant, and you don't need to think about thread safety. It's all immutable. But so once you go to the fixed array stuff, which requires more analysis, and also you have to start thinking about thread safety, you have to make a trade-off. Like, is this worth the extra complexity? I thought eventually that it's worth the extra complexity. So you need to pre-allocate these arrays and then calculate these indexes, where to read each local from. So basically, assoc bindings A1 becomes A set bindings 0, 1, if you decide that A is going to be in the 0th position of this array. And similarly, getting the binding becomes A get using an index. So this makes 15 times at least the locals part of the interpreter 15 times faster. But it does yield extra complexity. So this is a real piece of code from Psi. It's a macro which generates 42 functions, and each function is specific for one arity of a function that is going to produce. And you see a bunch of copying of values from one array to another array, and so it's a lot more complex. And so at this point, Psi has lost its educational value, because you could follow the examples at the beginning of this presentation, but this is harder to understand, certainly when you're first reading it. So yeah, that's a shame, but okay. So a little bit about interop. How is that implemented in Psi? So you have to provide a configuration, all the classes that you're going to support for your scripting environment. So here we support Java lang thread. We just passed the thread class. And we also define imports, which are the class names that are available by default in Clojure. But it's configurable in this environment. And then to make this work with GraalVM native image, you also need to provide a reflection configuration such that all the metadata of the classes are still available at runtime. And then Psi uses reflection to look up the right methods that are going to be invoked. And this invocation is done through reflection at runtime. So when you evaluate thread sleep 100, what happens is at analysis time, we can already see, okay, this is the class thread, but the sleep method actually depends on the type of the argument. So we cannot know this ahead of time unless we use the fact that it's 100 that it's passed here, but it's not always clear. But there is room for performance enhancements still in this area by resolving more of this type information at analysis time. But currently it's just reflection based. So another concern in Babashka is the binary size. Of course, I would like to, BB is a single binary. BB stands for Babashka, by the way. I didn't explain that yet, but that's what the binary is called. And of course, I want BB to be as small as possible. Right now, or for the last 2 years, it's been around 80 megabytes, and it's been fairly stable. It kind of depends on what GraalVM version I'm using, but things tend to become smaller with each release now. But this hasn't been always the case. But so that brings in a little bit variation, and of course, the majority of the size is what libraries do I include. So more built-in libraries and more built-in classes means bigger binary size. So that's also a trade-off to make. So it's not always clear beforehand which libraries are nice to have, and sometimes a user asks, like, can we have this library built into Babashka? But it's not always clear how many users will actually use that library. So this is why there's one of the reasons that Babashka has an extension mechanism called pods, which are external binaries that can expose functions to Babashka via an RPC mechanism. And it means compiling more GraalVM binaries. But these binaries can also be built using Golang or Haskell or whatever language, as long as the binary returns the right data. And below we see an example of using the instaparse library from a pod. And this works well if functions return data that can be serialized back and forth. If that's not the case, then this approach breaks a little bit. There are tricks to work around that by keeping state inside of this other binary. But in Clojure, a lot of the times, Clojure functions do communicate via data. So that's why this approach often works well. Okay, so Psi is not only used for native image, it also works on JavaScript. There's a couple of projects that also use the interpreter on JavaScript. One is called NBB, which is a sister project of Babashka, but it stands for Node Babashka. So you can do scripting on Node.js using Clojure. Again, it has a couple of useful built-in libraries. You can make playgrounds with your favorite libraries included for the browser. And there's also a project called Joyride, which allows scripting VS Code using Clojure. So you don't have to create an extension for every little thing that you want to do in VS Code anymore, but you can just write a little bit of Clojure to make VS Code as awesome as Emacs. Okay. Okay, one thing to make full circle. So Psi is also used in Condo, which is a static analyzer for Clojure, but some people write complicated macros in Clojure that Condo doesn't always understand. And so here we see an example of the usage of such a macro, which is flow. And so if you don't do any configuration, you see unresolved symbol original, and which is actually a local introduced by this macro. But if you write a hook, which is interpreted using Psi, you can instruct the static analyzer to understand this macro, and then you actually get very nice LSP support as well. Because if you stand on the double symbol there, you see that where it's defined is lighting up. So everything is clear to the editor now again. And this all works under GraalVM because it's running in Psi. So Psi is built on Clojure and JVM, GraalVM technology, which means we get a lot of things for free. It's getting better all the time. So this is a complicated example of spawning 100,000 threads to add up some numbers. And in each thread is sleeping for 1 second. And so this takes 1.6 seconds in total, which is similar to if you would run this on the JVM. But you can do this in Babashka, which is quite nice for something that replaces bash scripts. So we had our first Babashka conference last summer, which was very nice. There is a Babashka workshop as well that you can follow online or at various conferences. The last one was at Java Zone in Norway. There is a book online where you can learn Babashka specific things if you already know a little bit of Clojure. It's called Babuka by Daniel. He's also on this conference. And thanks everyone for sponsoring my open source projects. And my opinion, Clojure is the best language for scripting. That's it.